nuclear chemistry, it would have been added advantage for nuclear physics. Okay, I'll begin now. So already we have come across with a idea of the nucleus. No? We had a very good idea of the nucleus, sorry, atom. So what is the, according to Rutherford's model? And the Rutherford's atomic model. So what is the conclusion it was made like? The most of the atom is hollow, and the whole positive charge of the atom is concentrated at a very small region, and that what happened, he has called it as a nucleus. And next what he said, the electrons will revolve around circular orbit, or later part of Bohr's quantized, then what happened became elliptical orbit, Sommerfeld model, everything that one. So this particular thing will have a charge. This is called like a nucleus. And we are very sure that what is this? This electron is not like a particle, it behaves like a wave. It will have wave properties. That's what the Bohr's atomic model is, what we have concluded here. This electron, though it's a particle for us, but it is a wave, that one. It behaves like a wave there. Then, okay, now what happened? We have studied the atomic model, and hydrogen-like atoms is what we have confined ourselves. Now let's get into the nucleus. So what that nucleus made up of, that one? So the core part of the nucleus will be the protons as from the Rutherford model. Then later on in the 1935, the Chadwick one, like a British scientist, he has further discovered that the nucleus contains even the neutrons also. Neutrons also. This particular thing will represent by Z, and number of neutrons what happen will represent by N. So then based on this, what happen for a nucleus, we will put a terminology like the number of protons will indicate the atomic number. And the mass number, atomic mass number, or we just call only mass number. The mass number we denote by symbol A. And what is A? The sum of protons plus neutrons is called like the total mass of an atom, or total mass of a nucleus. What all the nucleus, what happen? We assume that electrons are not there. Even if you add mass of electron, will be negligible, no? When I say mass of atom or nucleus, both are one of the same, as far as at our level is concerned. So what is the mass of the nucleus? This mass of, like or mass number, what you can put it, A equal to the mass number we denote by symbol A, which is equal to number of neutrons plus number of the protons here. So then how to represent a nucleus? We do represent like this. This will be Z. So what do that Z represents there? This is one symbolic representation. So I think different books, again, they went for different way of showing this one. Different way of showing that one. So here some books they use like this. Both are one of the same. So X is some nucleus. X is some nucleus where its mass number and the atomic number. And some books, I think they have followed this method also. Anything. Okay, either of that one. So most of the, I think the books, they went for this particular representation. If you see the SC1 mall, they just took this particular way of representing that particular given nucleus. We just follow this one here. So here the prefix here, what it says, the atomic number of protons. This will give the total number of the sum of neutrons and protons. The sum of neutrons and protons, we'll call that as nucleons. So what are the nucleons? Protons or neutrons are called as, or both protons, you write it. Both protons and neutrons are called as nucleons. Both they are called as nucleon, that one. So what do this will give mass number or total number of nucleon that are present, and this Z will give the charge of nucleus. So if you put it like this, charge of nucleus, and this will represent number of nucleons. Now, what is our main purpose now? We have to study the nucleus. That's what the nuclear physics. The name of chapter itself is nuclear physics. What we have to study the nucleus and its properties. What do you mean by properties? Like, so definitely this nucleus. What are the properties of that one? Means, what is the mass of it? That's what we say mass number. Then next again, what is the radius of it? What is the density? What is the charge of it? Then what about the energy of it? Will it contains any energy? Then how that nucleons will be there, and how that nucleons will interact. Then will there be any interaction energy between them? And some nucleons are stable, unstable. Then what is the condition for them to be stable, unstable? So then everything will come under the properties of nucleus. Okay, what is the basically size of nucleus? It will be of order nuclear range, what we call it as 10 to power of minus 10 meter. So what is the nuclear range? The nuclear range is of order nuclear range, no? So this is what is of order 10 to power of minus 10 meter. So what can be the radius of the nucleus? It will be of order nuclear range, what we call. To measure such small distances, we introduce a quantity called as a femtometer. Femtometer. So this is equal to how much? 10 to power of minus 15 meter. To deal with such a small distances, what happens? A unit is called as a femtometer, like a millimeter, micrometer, nanometer, picometer. This is called like a femtometer, that one. And whenever say nuclear range is of order 10 to power of minus 10 meter. So the radius of the nucleus will be of order 10 to power of minus 10 meter, and the distance between nucleons, distance between protons or neutrons inside that will be of order 10 to power of minus 15 meter. Next question comes, what is the total mass of a, first we'll start with the mass. So what is the mass of a nucleus? Mass of a nucleus. So this is equal to mass of nucleons into number of nucleons here. What is the mass of, usually mass of proton, neutron, no? So what is the mass? Will it be in terms of kg? As we know, mass of proton is how much? Around 1.67 up to, I think, around, okay, this one, 3 decimal places, I'll write. This will be minus 10 to the power of minus 27 kg. Mass of neutron will be 1.674. 74, yeah. Some books they're given 75, and what we have is mass of electron 9.1 into 9.11 or 0 into 9.109 into 10 to the power of minus 31 kg. So these are the mass of the particles what we are able to measure now using some experimental data. So dealing with quantities of such a very lower value will be very difficult in calculations. No? For that purpose, we bring atomic mass unit here. 1 AMU, or this called like a 1 U. So what it is equal to? 931 point. What is 1 AMU? How to define 1 AMU? It's like a unified atomic mass. It's like atomic mass, unified atomic mass unit here. So it is what is 1 AMU is equal to 1/12 of the mass of neutral carbon atom in its lowest energy state which contains 6 protons, 6 neutrons and 6 electrons. This is one reference is what we are taking. 1/12 of the mass of neutral carbon atom in its lowest energy state, which contains 6 protons, 6 neutrons, and 6 electrons, not carbon nucleus. I think this is, please do notice here. Huh? In exams, they may test you with this carbon nucleus, carbon atom. Carbon atom is telling. That is called as the 1 AMU. We express that as 931.478 mega electron volt by C square. Then how to how to express mass in terms of energy? I think all of you know E equal to mc square. E equal to mc square. So from that, what happened? Energy equivalent of any particle, what happened, can be determined here. So there's one basic idea of there's a unit to measure the mass of a subatomic particles. Rather than kgs, no, we prefer to express in terms of EMU. Okay, now so what we're planning? So what we have brought it, we have brought to measure distances and also to measure mass. First we brought a units here. So first here, so what is the first thing? The first one is atomic distances, you write. Second one is atomic mass. So like this, what happened? We are ourselves designing new things because we are dealing with a subatomic particles where the separation between them will be of order very small. So 1 unit femtometer. Then there are tiny particles. So we can't use kg in calculations. So better to bring EMU. The reason for that, why we should not go for kg, because in calculations, even up to 6 decimal place matters here. But if you convert that into AMU, I think you'll be on safer side. If you convert that into AMU, so what's happened? It will be much easier for us. So we need to bother till 6 decimal places. Why we are bringing atomic mass unit is if you're dealing the problem with only in kgs, no, up to 6 or 7, or sometimes to more accurate, up to 8 decimal places here to work out. I think doing multiplication, division, or subtraction, addition, mathematical operations with the 8 decimal places will be very big headache. No? Instead, if you convert that into AMU, okay, up to maximum 3 or 4 decimal places, if you can take it, is almost the error will get minimized here. So there's a reason why we are bringing atomic mass units. Got the idea? This one. After this, what about the protons, neutrons? How they will be? The third one, location of nucleons in nucleus. Means how do they will be located? So if for this, what we have, suppose that there's a nucleus. This particular thing is like a clusters. we can't move. Better to draw it. Very difficult to draw. I'll show it by another method. Nucleons, as such, what happened? We are assuming it to be spherical. So still, the neutrons, even the electron, all is what in the books also they are shown spherical. So I am also going to do the same thing. Wait, wait, some. There's a plane diagram. You should assume the 3D diagram here. Small, tiny beads or tiny balls. So if you just join them, 3D diagram, like this will be a cluster. So these nucleons, there's a rough diagram I'm putting. Blue color is what? We'll go for protons. There is no any like a first protons will be there in the inner layer, outer layer neutrons, nothing to do that one. We can put it like this. So so what is the atom? What is the nucleus? So it's made up of cluster of nucleons. So this red color, let me call them as, and this one. So this will be neutrons, and this is the protons. You just assume that tiny balls. So in books what pen they written PN like that. I'm just showing the colors here. This will be, so this will be the radius. So yeah, okay, this show like this. So this will be the radius of the rough diagram it is, and there is no any specific boundary for nucleus. It should not be spherical, but it's a practice of showing it spherical. There should not be any specific boundary. That one. So how actually the boundary will come like this, no? Should not be a perfect space circle. So we have a practice of showing in book like circle inside that nucleon they show it, and they are spherical balls. I think this is something very important. Small, tiny, spherical particles. These are the nucleons. and they will obey the Pauli's exclusion principle. The nucleons, what will happen? What are the things? First, regarding nucleons, we'll write it. Nucleons, what happen? They have mass. Then what about the proton? Proton will have their mass and they interact with each other. They interact with each other. Next again. Protons, what happen? Protons are the particles which will have mass and charge. What about neutrons? Mass and electrically neutral. And neutral. Or say they're not having any charge, that one. So these are about the protons, and both protons and neutrons are fermions. And they obey the Pauli's exclusion principle here. So both protons and protons obey the Pauli's exclusion principle. Now, what that principle says, no two protons or two neutrons can have the same quantum state. But in a one quantum state, there can be one proton and one neutron. That one means here, like if there's a quantum state, so there's a quantum state, and there's a quantum state. So here what happened? It's not possible to be like this. Not permitted. Then this is not possible. But this is possible. This is permitted. In a given quantum state, two protons cannot exist, two neutrons, but one proton, one neutron can exist here. So like this, they obey the Pauli's exclusion principle. Of course, we don't study this. Even what happened, you have to apply the quantization rule, law of quantum mechanics, even inside the nucleus also. They'll also obey the same thing, quantization. So we don't go much because again, we have to study the different nuclear models, which is not part for syllabus. So this is what red we have took, no? Neutron, neutron, proton, proton. This will be proton, neutron. Not permitted. What is that dotted line? Quantum state. This is permitted. This is next again. After this, the what about the this particular nucleons? So they'll exert force on each other. A given nucleons, what happen? They'll exert a force on each other, and that force of interaction between nucleons is nothing but like what we can call nuclear force here. So further, nucleons, they interact with each other or exert force on each other. So let's get into the